Here we go. So 4.2 polynomial functions and models. Basically with this unit, we are just diving deeper into polynomial functions. So if you have taken Algebra 2 already, then it should be somewhat of a review because it's just about vocabulary and appropriately using that vocabulary, okay? So our objectives here are to be able to understand the graphs of polynomial functions, evaluate and graph piecewise defined functions, and use polynomial regressions to model data. Again, if you're in pre-AP Algebra 2, we spent so much time on regression models that I feel like you guys should be able to live and breathe what a regression model is and how to find it. You're welcome. So our main focus is to be able to identify the number of zeros. So our zeros are the same thing as our roots, right? Our roots are where do we cross the x-axis. So when you see the word zeros or roots or x-intercepts, they all are the same thing. They're synonyms for the same thing, okay? The number of zeros of a function can be equal to the exponent or can be less than by a multiple of 2. So when you look right here, if I have a quintic, who wants to tell me what you think a degree of a quintic function is? What is it, Larry? 5. Quintic. Like when people have quintuplets, how many babies do they have? 5. So a quintic function is a fifth degree polynomial, okay? I am a fifth degree polynomial, which means that I can have up to 5 zeros, which means I'm going to cross the x-axis 5 times, or I can have 3 or 1, okay? I'm going to have to cross at some point, right? And the reason why we can have 3 or 1 is because of what's called multiplicity, which is in the next unit, so we're not going to worry about it now. To find the zeros, you factor the polynomial. Your zeros are from your factors, okay? So your zeros are your factors. Meaning that if I know that I have a 0 at x equals 1, a 0 at x equals 2, at x equals -3, then I know that my factors are going to be x minus 1, x minus 2, and x plus 3 because our x's are liars, and that's why they're x's, okay? They're going to always be the opposite of each other. So your zeros and your factors are opposites. Okay, next are your critical points. Our last section, 4.1, hopefully you did your quick check. That was over our extrema, right? So our relative, local, absolute, and global, correct? So our extrema, those are called turning points. When we call them turning points, that means you're giving me the ordered pair. You're telling me where your relative max and min are. So it's the x comma the y. So if I ask for the turning point, you're giving me the ordered pair versus when I'm asking you for your extrema, you're giving me what value only? The extrema is only the what? Of what though? The extrema is your, which value? The y's. There we go. Your extrema is your y's, okay? X marks the spot, but y is why you're there. So when I ask what is the extrema, that's your y. That is why you're there to tell me what it is, okay? All right, so those are our vocabulary so far. So we have our critical points are our zeros and our turning points, okay? Next, our types of our function. Y'all remember Bob? If I was your teacher, you've had Bob before. Bob has 4 dance moves, right? Bob's 4 dance moves depend on whether you are an odd degree or an even degree, correct? Yes, we all agree. So if you are an odd degree with Bob, you can always stand up and do his dance moves with me. No, don't be shy. If you're an odd degree, Bob is either staying alive, right? All day long. That's all you can do is opposite behaviors, correct? You're staying alive. If you're an even degree, Bob is waving his hands in the air like he doesn't care, or he's shimming on down, right? That's because your leading coefficient. So if your leading coefficient is positive, it tells you what your right side is doing, right? So if my right is going positive and I'm odd, we're going to be doing the opposite, and that's why we're staying alive, okay? If my leading coefficient is negative, my right is going down, and I'm odd, so it's being the opposite, and we're staying alive this way, right? Even degree, again, right side first, positive, even behavior, waving my hands. Even degree, negative leading coefficient down, even behavior, shimming on down. That's it. Those are Bob's dance moves. Boom, boom, call it a day. Your number of turning points. So your turning points is at most the number at your turning point minus 1, okay? So your degree minus 1, I'm sorry. So whatever your degree is, minus 1 equals your turning points. Okay, so if I am a quadratic, for example, that means that I'm a second degree, right? Minus 1 equals 1 turning point, which makes sense because the shape of a quadratic either is going to have 1 at the bottom or 1 at the top, correct? At most. All right. Do you think you could find, if I told you the turning point, could you tell me my degree? Yeah, because it's an equation. It's going to be the opposite, right? So because of the degree minus 1, that means that TPs, I know some people say it stands for toilet paper, but whatever. TP in this case is for turning point. TP is going to be your degree plus 1. And I had to squeeze that in there because I underestimated my space. Okay. All right. So those are our vocabulary words. Now we're going to apply the vocabulary words. Okay. If you want to like do a little sketch of the graph that you're about to see, go for it. But we're going to apply the vocabulary words to this situation. All right. Here we go. Determine the number of turning points. So I'm determining the number of turning points, which means I'm looking for what? My maximums and minimums. I'm looking for my maximum, my mins. I'm looking for my extrema, correct? So I'm identifying my extrema. So my extrema have a max here, I have a min here, and a min here. Okay. Just a quick review of 4.1. Do I have a global anything? What do I have a global of? I have a global minimum. Thank you. See, look, Piper, aren't you glad you stayed today? No, I'm glad you stayed. Yes, they did. So in their defense. All right. So number of turning points is TP's equal 3. Agree? All right. And then our estimated x-intercepts. How many x-intercepts do I have? I have 4. So we have 4 x-intercepts. And our x-intercepts are at -4, 0, at -2, 0, at +2, 0, and at +3, 0. All agree? All right. From this, next, we're going to state our leading coefficient. Which side of my graph determines my leading coefficient behavior? It's the right. The right side of my graph determines my leading coefficient behavior. My right side is heading towards positive infinity. Because my right side is heading towards positive infinity, that means that my leading coefficient is positive. Make sense? The right side is heading towards positive infinity, so my leading coefficient is positive. All right, now I have all this information. I should be able to determine the degree of my function, okay? The first thing you're going to ask yourself, is it even or odd? So the first question you answer, is it an even function or an odd function? What do we have? What's my dance moves? I'm waving my hands in the air like I don't care. So it's a even function, okay? After I've determined that, that means that it's either going to be 2, 4, 6, 8. Who do we appreciate? Keep going from there. So second thing is to decide, based off of either your turning points or your x-intercepts, what is the degree of my polynomial? Does it matter which one I use? Nope, because they're going to be the same. All right, so if I chose to use my turning points, I would determine my degree by adding 1 to that. Does that make sense? So if I was to use my turning points, my degree equals 3 plus 1, which is 4, right? If I was to use my x-intercepts, my degree is how many x-intercepts I have. And how many x-intercepts do I have? 4. Notice that these values are the same. So this is a 4th degree polynomial. So what we have here is a positive 4th degree polynomial. So notice it's not actually calculating, it's a use of vocabulary. Do you understand the vocabulary and can you identify the vocabulary? So to find your turning points is your degrees minus 1. If you have your turning points to find your degrees, it would be plus 1. You're welcome. Okay, yes? All right, so this is if the graph is given to you, that's how we do it. The next example we're going to look at is if you have to create the graph yourself, how do you find these values, okay? So we're going to be using our calculator to determine those. So if I have to create the graph myself, how is the calculator going to aid me in this process, okay? So let's open up Homegirl Sylvie. Hey, girl. I'm going to turn her on. I'm going to reset. Second plus 712. Okay. So here we go. I'm going to put in my function into y equals. So we have y equals x to the third minus 4x. Okay. And it says for me to find my x-intercepts. Now, graphically, when this graphs, it is fairly easy for me to find my x-intercepts, correct? Clearly, I can see, oh, it's at -2, it's at 0, and it's at +2. If it wasn't as friendly to do so, then I would use the second trace feature to find my zeros. Does that make sense? So I would go second trace and go to 0. Once I go to 0, I'm going to start from the left because we read graphs from left to right. I'm going to go to the right now, and it's going to say, oh, here you go. Your zero's at -2. And that will repeat that pattern until I found all of my zeros, okay? Now, we all like it when it's easy to read, and this is pretty easy to read. So our zeros are at -2, 0. We're at 0, 0, and we're at +2, 0. All right, questions about using your calculator to find your zeros. All right, next is going to be finding our turning points. Remember, when we're finding our turning points, essentially all we're finding are our local extrema, right? What are your local extrema? So I'm looking for, are they max or are they min? The difference is because it's the turning point, you're writing the x and the y. Turning point just means you are going to have a point, an ordered pair. So your solution would be an x comma a y, okay? So you have to decide when you're searching on here, is it a max or a min that you're searching for? So my first one is a max. So I'm going to hit second trace, and I'm going to go to where it says max. We see that? And then I'm going to go to the left of it, hit enter. Then I'm going to go to the right of it, hit enter. And it's going to tell me, here's your turning point. My turning point is at 1 and 155 thousandths, comma 3 and 79 thousandths. 3.079. I forgot my negative. Oh, thank you. Yes. Okay. And we're going to do it again. Okay. So doing it again, we are now finding our minimum, right? So second trace minimum. And I'm going to get close to the left side of it. To the left, hit enter. I'm going to go to the right of it. Oh my gosh. Why are you running from me, Sylvie? Okay. Oh, is that why? I've done nothing to her. And we're at 1 and 155 thousandths. And we're at -3 and 79. Okay, those are my turning points. It said to the hundredth, but I went to the thousandth, so ignore that. But you get what I'm saying. Yes? Okay. The other thing is if you're not strong at rounding, if it tells you what you're rounding to, so it says to the hundredth, I could have went to mode first, went to float, and told my calculator I need it to be 2 digits only. And so when I go over here, it will automatically find those values to the nearest 2 digits. So if I was to do my min, enter, go over, enter, enter. So she would automatically find it to the nearest 2 digits for me. Okay. So if you already know what you're rounding to, then you can set Sylvie or whatever calculator you have to do the rounding for you. Cool? Okay. So now it says use your turning points to approximate any local extrema. Well, my turning points are going to approximate my local extrema. Local extrema, again, means that I'm only putting the what value? Extrema means I only care about the y value, okay? When you're referring to extrema, sorry, let me write, please. You're asking for the y value, okay? So my local max is what? Which is the highest? What is it? 3.079. My local min is negative 3.079. Okay, and they're local because this is an odd function, right? And this odd function is going forever to positive infinity and forever to negative infinity. All right, how do we feel about creating the graph and identifying important critical points and being given the graph and identifying? Doable? Perfect. Okay. Because when I'm teaching in your other class, you'd be having other conversations with your table. No. Makes sense in this class. What makes sense? I can't like. All right. Okay, here we go. Tell me, what's the degree? What is it? Fourth. How do I know it's the fourth? It's the highest exponent. Okay, the highest exponent. What is my leading coefficient then? Negative 1/2. My leading coefficient is negative 1/2. Okay. When I've graded your assignments before, I've seen that in the previous people that they think leading coefficient means your highest coefficient, and that's not what leading coefficient means. Leading coefficient means it's with the highest variable power. Okay. So you're looking for the coefficient with the highest variable power, not the greatest coefficient. Okay. All right. Now, because I have these two pieces of information, can I say what my end behavior is? Yes. So you always start with the right. Okay. When you're starting with the right, what you're saying is as x goes to positive infinity, y is doing what in this case? Y is doing what? What's your leading coefficient? Negative. My leading coefficient is negative. So therefore my y is heading towards negative infinity. Okay. That is an ugly infinity. Can't even accept it. Better-ish. Okay. Again, because my leading coefficient is negative, my right side behavior is negative. Okay. Your left side depends on your degree. So your left side depends on your degree. And because our degree is even, that means my left side is going to be doing the same behavior as the right side. Does that make sense? Your left is as x goes to negative infinity, your y is going to be going to negative infinity. Okay. Okay. All right. Yes. They're in because they're even, they're doing the same behavior. So if my right is going down, my left has to also be going down. I'm shimming down. Okay. They have to even behaviors behave the same. Okay. Again, vocabulary. Did I do anything else but apply my vocabulary? No. Okay. Questions about this one? Mm-hmm. Yep. Okay. The left is telling you, so like, because it's going right, that's why your x is a positive infinity, right? Because when you go to the right, those are your positive infinity, right? When you're going left, you're heading towards negative infinity. So these two are going to always be the same. What changes is what are your y's doing, right? That's what's changing. All right. We're going to now move on to our regressions. Regression means that we're using technology to evaluate and decide what best represents this function, okay? With this regression model, I am not asking you for the full function. I'm asking you, after analyzing your scatter plot, which function would be a better model for it. Does that make sense? Okay, so let's take a gander here. So I'm going to open up Sylvie. If you, again, have had Algebra 2, you should be comfortable finding the regression model. I do understand that non-pre-AP Algebra 2 does not learn regression model in the 84. Pre-AP, you do learn it in the 84, so you should be comfortable. If you did not have pre-AP, then please make sure you follow along and ask questions, okay? All right, so once we reset our calculator by pressing, how do we reset? Second plus 712. Now we're cleared. We're going to press stat. Stat is where we're putting all of our information at. So I'm going to press stat edit, and I'm going to put in my values. So we have 1830. We have 3 9/10. I'm sorry, I put that in the wrong spot because it didn't go over. I'll just do it all at once. I'm going to do my X's first. 1830, 1900, 1950, and 2000. Okay. So what we're measuring here is the immigration rate per 1,000 U.S. population during each year. All right. Now we're going to put it in we have 3 9/10. We have 10 4/10. There was a huge immigration flux in 1900. Anyone knows why? The what? Industrial Revolution. Okay. So now we have these are all the values. Mm-hmm. Okay. All right. So we put our values in. Now that we put our values in, we need to be able to look at our scatter plot because it's asked, could a linear or quadratic function model this data? To turn on our scatter plot, we're going to go to y equals. There's other ways, but this is going to be your fastest. So you go to y equal, and you're going to arrow up to where it says plot because we want it to be plotted. Does that make sense? So we're going to arrow up, and you're going to press enter. That's how you turn on your plot. You know that it's turned on because if you arrow down, it should be bolded. Okay? After we do that, we then are going to press zoom. Okay? So we're going to press zoom. And the reason why we press zoom is because we want to see our stat, our statistical data that we put into our stat edit. And we're going to press 9 to get there. And then lo and behold, bam, here's our scatter plot. Okay? So I'm going to redo those steps again. So I went to stat, edit. I input in my X values and my Y values, correct? After I put that data in, I went to Y equals. I arrowed up and turned on my plot. And I arrowed down to make sure it's on. Oh no, it's not on. So I'm going to go back, press enter. And when I arrow down, notice that it is bolded, correct? We then are going to go to zoom, and we're going to go to zoom stat because I want it to graph my points for me. To get to zoom stat, I either can arrow down or press 9. And now here are my points plotted for me. Okay, looking at my scatter plot, is this linear or quadratic? Is it linear or quadratic? Or neither? Neither, it's not. Could it be linear? No. Because if I was to, linear meant that I would have a line, like it would be along a line situation. Is that working? No. Okay. Quadratic would mean that I would have this type of situation happening. Is that happening? No. So does linear or quadratic work for this problem? No, it does not. Okay. So the answer here would be no to linear and no to quadratic. Agreed? All right. Now, looking at what I have here, if I was to try to connect what would be a good model? So trying to connect all my points, pretending that I can go through them. I would have to create something of this nature, right? It would have to be this option. It also, that's pretty much it. I can't really think of anything else. So based on what I created here, what degree would this have to be? It would have to be one, it had to be odd. How do I know it has to be odd? Because they're going in different directions, right? We're staying alive, so it has to be an odd degree. Agreed? Okay. And then two, I'm going to look at my turning points. I have a turning point here and a turning point here. How many TPs do I have? 2. So in there, I have 2 turning points. Because I have 2 turning points, that means a bare minimum of my degree would have to be a third degree. Does that make sense? So a third degree polynomial is what it would have to be. Okay? Would it be a positive or negative? It would be positive because what is the right side of my function heading to? It's going up. It's heading towards positive infinity. So it would have to be a positive. So I would have to have a positive third degree polynomial. Does that make sense? Yes. And it would have to be positive. Okay? So my function would be that. Agree? Did we see what we did there? All right. So okay. So to confirm what I said, we traced it out. We saw where we're going. We're going to confirm. So we go to stat, and this time we're going to go to calc. It's not asking for it, so I don't have to write it out, but I can confirm whether it is a third degree. Third degree polynomials are called cubic. Okay, a third degree polynomial is called a cubic function. And so see number 6 where it says cubic regression. We're going to click on 6 for cubic. It's going to ask you, is your X list your L1? Is your X list your L2? Yes. Frequency list does not matter. This is where it's important to store. That's because we want it to graph it for us, right? If I want it to graph it for me, I'm going to press alpha trace 1. And I hit calculate. And now it's going to say, okay, cool. Notice that I do have a positive. And when I go hit graph, it's going to plot my points. And it's going to show the model that it said would best fit my data. And that's a pretty good fit, right? It went down, it's coming up, and bam. Did it hit most of my points? Yes, it did. Okay. Now, I would like to point out that this isn't the only option. Okay. So this could also have been a quartic. So by showing you that, I don't want you to do it. I'm just going to show you. If I went to stat calc, I could also test out a quartic model. If I press 7, I'm going to store this one, though, in my Y2 so we can see the difference. And I'm going to hit calculate. And it's like, oh, no. It's just something doesn't work. What doesn't work? It's outside of your domain. Error, error. And I'm like, well, what's wrong? Why is it outside of my domain? I have no clue why it is. But it wouldn't let me graph it. It said that didn't work for your situation. And I'm like, okay, cool. So this is a good fit. Cubic. Okay. I can test it out and the calculator will help me, right? If I have the calculator, it's meant to be a tool. Use the tool to its fullest. Okay. All right. So I'm going to show you guys from start to finish how this should be a 90-second situation by the time you are comfortable with the calculator. So I'm going to reset. And I'm going to go through the process of completely putting in from start to finish, and you can feel free to time me. So, oh, I have a regression model. Why are you throwing your computer? Okay. All right. Awkward. So moving on. All right. Are we ready? Okay. Here we go. So I'm going to go to stat. I'm going to go to edit. I'm going to put in my x's. I'm going to put in all of them at one time. And we have 2000. And then I'm going to put in my y's, 3 and 9/10, 10 and 4/10, 7/10, and 3 and 2/10. And bam, I'm going to go to y equals, turn on my plot. I can go to zoom. I'm going to look at my plot. From my plot, I see go boom, 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 boom. Like, oh, good. That looks like a cubic. Go to calc, go to cubic, and go down, down, down. And I would like it to store, alpha, trace, store it, and calculate. Now I have my equation, and I have my graph, and now I know I'm right, and I'm done, and all is great. Okay? That is the process every single time. Okay? It's not meant to be a long, drawn-out process. If you don't practice it, then that's where you're going to get stuck at. Okay? If you don't practice, you're going to get stuck. Got it? All right, questions about the regression. Right now, our job for the regression is just identifying which one works best, right? I'm not asking for the equation. I'm just asking which one works best. Got it? All right. Up next is piecewise. So we're going to watch, I'm going to pause for a moment on my talking, and we're going to watch a quick little video from one of the most soothing voices, I feel personally, that teaches, aka Dr. Khan. Where'd my video go? My video. We're going to go. Here we go.
Now we're used to seeing functions defined like h of y is equal to y squared, or f of x is equal to the square root of x. What we're now going to explore is functions that are defined piece by piece over different intervals. And functions like this are, you'll sometimes view them as a piecewise, or these types of function definitions, they might be called a piecewise function definition. And so let's take a look at this graph right over here. This graph, you can see that the function is constant over this interval for x, and then it jumps up to this interval for x, and then it jumps back down for this interval for x. So let's think about how we would write this using our function notation. So if we say that this right over here is the x-axis, and if this is the y, it is equal to f of x axis, then let's see, our function f of x is going to be equal to, let's see, there's 3 different intervals. Give myself some space for the 3 different intervals. Now, this first interval is from not including -9. I have this open circle here, not a closed-in circle. So not including -9, but x being greater than -9 and all the way up to and including -5. So I could write that as -9 is less than x, less than or equal to -5. That's this interval. And what is the value of the function over this interval? Well, we see the value of the function is -9, the constant -9 over that interval. It's a little confusing because the value of the function is actually also the value of the lower bound on this interval, right? And it's very important to look at that. This says -9 is less than x, not less than or equal. If it was less than or equal, then the function would have been defined at x equals -9, but it's not. We have an open circle right over there. But now let's look at the next interval. The next interval is from x is greater, or -5 is less than x, which is less than or equal to -1. And over that interval, the function is equal to, the function is a constant 6. It jumps up here. Sometimes people call this a step function. It steps up. It looks like stairs to some degree. Now, it's very important here that at x equals -5, for it to be defined only one place. Here, it's defined by this part. It's only defined over here. And so that's why it's important that this isn't a -5 is less than or equal to, because then if you put -5 into the function, this thing would be filled in, and then the function would be defined to both places, and that's not cool for a function. It wouldn't be a function anymore. So it's very important that that when you input -5 in here, you know which of these intervals you are in. You can't be in two of these intervals. If you are in 2 of these intervals, the interval should give you the same value so that the function maps from one input to the same output. Now let's keep going. We have this last interval where we're going from -1. We're going from -1 to 9, from -1 to +9. And x, it starts off with -1 less than x because you have an open circle right up here. And that's good because x equals -1 is defined up here, all the way to x is less than or equal to 9. And over that interval, what is the value of our function? Well, you see the value of our function is a constant -7. A constant -7. And we're done. We have just constructed a piece-by-piece definition of this function. And actually, when you see this type of function notation, it becomes a lot clearer why function notation is useful even. And hopefully, anyway, hopefully you enjoy that. I always find these piecewise functions a lot of fun.
All right. So basically, piecewise function is how our world operates, right? Our actual world is nothing is perfectly linear, nothing is perfectly quadratic, nothing is perfectly exponential, right? And so because of that, we have to be able to accurately model the world around us. And that's where piecewise function come into play, okay? So let's talk about how to evaluate a piecewise function. Evaluating a piecewise function means that you have to pay attention to your lower bound and upper bound of your piecewise and where they're equal and not equal, okay? So in elementary, you learn that when there's an open circle, do y'all remember that? Open circle means that it is less than, right? Or greater than, which means that it's not equal at that point. Okay, it's just less than or greater than, right? A closed circle means that you are less than or equal to or greater than or equal to, and you are equal at that value. You are included in that value, okay? As Dr. Khan said, that in order for this to be a function, you cannot be equal at the same x value in an interval, okay? So if you look here in our function, notice that I am at -2 here, I'm not equal, right? But I am equal on the second interval, okay? I'm equal here at 1, but I'm not equal here at 1, okay? You cannot have double equality. Otherwise, it will not be a function, okay? Because your x is your input, and it cannot repeat when it's a function. Make sense? All right, so we're going to talk about evaluating. Evaluating just simply means you are plugging in. When you hear the word evaluate, that means to do what? Plug it in, okay? It means just plug it in. The only thing is, you have to now decide which piece of this function am I plugging it into, okay? So we have 3 pieces. I like to label my pieces. This is piece 1, piece 2, and piece 3. Based on the interval of your lower and upper bounds, you're going to determine which piece to use to evaluate, okay? So when we look right here, we have -3. -3 fits which one of our intervals? Which piece of the pie? 1. So that means I'm going to use equation 1 because -3 is equal in equation 1. Do we see that? So to evaluate f of -3, I'm using 2 minus -3, which equals 2 plus 3, which is 5. Does that make sense? Yeah? All right. So let's do -2. Which piece of my function am I using to evaluate -2? And why am I using 2? It's just less than. And 2 is where it is equal to. So we're using the second piece of our piecewise to evaluate. So f of -2 equals 1 minus -2 squared, which equals 1 minus 4, which equals -3. Cool? All right. Our third piece, our third x is 1. 1 falls on which interval? 2. Okay, it's on 2 because that's where I am equal to, right? On 3, I am just the lower bound. There's no equality right there. So we're going to plug that in to 2. So f of 1 equals 1 minus 1 squared, which is just 0. Still good? We're catching on? Yes. Okay. 2. What piece of the piecewise function is 2? 3. Your lower and upper bounds on the inequality. Okay. So 3, which means I'm using x cubed. So to find f of 2, I'm using 2 to the third. And what is 2 to the third? 8. Perfect. And that's how you evaluate. Okay. The key part of evaluating is establishing where that x is defined at, right? Which domain contains that x? If it doesn't contain it, can I use that piece? No. Capiche? But we're good now? Okay. So this is evaluating. The next piece is how to graph a piecewise. So before we go on to graphing, we need to make sure that we're comfortable with evaluating. Are we comfortable with evaluating? Okay. Yes. Okay. All right. Now we're going to graph a piecewise function. Okay. When you're graphing a piecewise function, what matters are your breaking points, which is what your lower and upper bounds are. I call them breaking points. Okay. So each inequality is going to have a breaking point, at least one breaking point, because it could be one that says x is just less than 3, which means everything to the left or left of it, right? But I have each one of these are my breaking points. My breaking points are my upper and lower bounds. So -4, -2, -2, 2, 2, 4. Those are the points that matter. Those are the pieces that matter. Okay. So these are the breaking points for my first piece of my piecewise. These are the breaking points for the second piece, and these are the breaking points for the third piece. You're going to do them piece by piece to create your function. Okay. For some people, it helps to highlight on your if you're drawing, it helps to highlight where those breaking points are. So I know that I'm putting something, and I really can't draw straight lines. Like, it's really tragic, but so I thought if I made a dash, it would look like I intentionally struggle. So I'm at -2, -4, -2. I'm at, that is not +2. Yep. Oh, got a little wavy there. Oh, a little more wavy. I swear I'd be thinking my hand is going straight down. All right. So those are my breaking points. Now we're going to start finding the values that lie on those breaking points. Okay. So we're going to start with our first piece. So using my first piece, my x's that I'm evaluating are -4 and at -2. Because -4 is equal to, I know that it's going to be a closed circle. Because -2 is also equal to, I know that it's going to be a closed circle. Make sense? So yes, because they're both equal to. Okay. So now we're going to plug them in. So we're going to evaluate. This is your evaluating. So I'm plugging in. So I have 0.5 times -4 squared, which equals 0.5 times 16, which is 8. I have 0.5 times -2 squared, which equals 0.5 times 4, which equals 2. After you find your behaviors at your breaking points, you're going to plot them based on what you said. Is it a closed or an open circle? They're closed circles. So I'm going to go to -4 and go to 8, -4, 8, and put a closed circle. I'm going to go to -2, 2, and put a closed circle. And I'm going to connect those two pieces. Those two pieces are now connected. My first piece is now done. And then I'm going to repeat the same process again for the next piece. I should have 3 pieces because how many pieces are there in my piecewise? 3. Okay, so now we're going to do piece 2. Piece 2 is at -2 and at +2. At -2 and +2, I have strictly less than, which means that each one of these values are going to be open circles, right? And now we're going to evaluate. Well, it just says that it equals what? Equals x, so it's going to equal itself. So I'm going to go to -2, -2, and I'm putting in open circle. I'm going to go to +2 and +2, and I'm putting in open circle, and then I'm going to connect them based on their behavior, which is linear. So they are now connected. How we feel? Pretty good? All right. Now we're going to go to our last piece. So piece 3. Oh, I forgot this is my no writing zone. Okay. And our lower bound is 2. And at 2, it's a equal to. So it's going to be a closed circle. Our upper bound is 4. And it's another equal to. So it's going to be closed circle. We're going to evaluate. So we have 2 squared minus 4. What is 2 squared minus 4? It's going to be 0. Then we have 4 squared minus 4, which is going to be 12. So on my breaking point at 2, I go to 2, and I'm staying at 0, and it's going to be a closed circle at 0. And I go to 4, and it's going to go up to 12, and it's a quadratic, so it's going to have a little bit of a curve all the way till I get to the. And that's how you graph a piecewise. Okay, you literally have to do it in pieces. All right, the math itself isn't difficult. You just have to remember the process. Identify your lower and upper bounds, identify their equality or lack of equality, and then plug in. How you feel? Not that bad. We feel good about graphing piecewise? All right. Huh? What's wrong? Oh, I need sleep. All right, here we go. On the next piece, we are looking at function f. So function f is f of x equals 2x from 0 to 4. And then we have -1/4 x squared plus 4x minus 4 if 4 is less than or equal to x, which is less than or equal to 12. Now, I'm going to be honest with y'all. This graph and this table, but the graph and the function itself do not go together. Like they don't match. Like the values do not make sense. So we're not going to rely on the image so much. I'm just letting y'all know that. Does that make sense? It is not graph to scale. It's what came with the textbook. But basically, you are describing a fish harvest, okay, in a region. And there is a certain limit to overfishing, correct? If I am fishing and we're doing it correct and there's the right amount of boats, notice that there's a constant return. Do we see that? So right here, as long as we stay from here to here, there's a constant return. Okay, that's what this piece of the function is representing, that 2x. Okay, then once we get here, this is our point of diminishing returns. Okay, your point of diminishing returns means that at this point, things start getting a little weird, right? We start reaching the zone where we are not going to end up making or being able to replenish the fish that's coming out at the rate that we're taking the fish. Does that make sense? We're now going to be in a loss of fish. So at this point, we reach our diminishing returns. And okay, so we start dropping back down. Our job is to answer these questions. Again, we're not going to rely so much on this guy. Does that make sense? because it is not, the values are not accurate. We're going to rely on the function that's given to us. And this is just a visual of what we're looking for. Cool? All right, so up first, it says evaluate f of 6 and interpret your answer. So if I'm looking for f of 6 is an x value. Because it's an x value, I first have to decide which piece of my piecewise am I using to evaluate f of 6. So which piece of my piecewise will I use to evaluate f of 6? I'm going to use piece 2. So using piece 2 to evaluate f of 6, we end up with f of 6 equals negative 1, 4, 6 squared plus 4 times 6 minus 4. If you do this in the calculator or in your head, you get 6 squared is 36. 36 divided by negative 4 is 9. 9 plus 24, and negative 9 plus 24 is negative 15. It's 15. 15 minus 4 is 11. Okay. So you get 11. That 11 represents thousands of tons of fish. Does that make sense? So if you have 6, which represents 100, 600, so interpret, if we have 600 fishing boats out, then we're going to expect 11,000 tons of fish caught. Fish is not spelled like that. Okay, make sense? And that's what it means to interpret your answer. So what do the values you got represent when you pertain to this problem? Because you're not going to be in a presentation say f of 6 is 11. And people are like, what? What does f of 6 of 11 means? You're like, oh, yeah, the 600 fishermen, if they go out, we're going to get like 11,000 fish. Okay? You have to be able to interpret, right? Next, it says solve f of x equals 6 and interpret the results. So if I want to solve this time, instead of me being given my x, I'm being given my y. Okay? So we're being given our y. And when we're given our y, it's going to be like us having to work backwards. Does that make sense? You're trying to figure out what x value would produce 6. And what does that 6 represent? That represents 6,000 tons of fish, right? So how many boats need to go out in order for me to get approximately 6 tons of fish? All right. Essentially, you're going to take each one of these equations and set it equal to 6. Based on setting each equation to 6, you're going to see which one satisfies the domain. The one that satisfies the domain is your result. The one that doesn't is not. Is incorrect. Perfect. So you end up with, you're going to test 2x equals 6, and you're testing negative 1/4 x squared plus 4x minus 4 equals 6. Okay? You can clearly do this by hand, right? If I have 2x equals 6, what is x? X equals 3. Does that satisfy the domain? Does that satisfy the domain of piece 1? Yes, it does. So guess what I don't have to do? Do I have to do the next one? No. I could just to make sure, but is it necessary? No. I see that, oh, I'm done. I got 3. So what does that mean? So the answer would be, there needs to be 300 boats of fishing, right? In order for us to get 6,000 tons of fish harvested. Okay. If the first one didn't work, what would I have to do? Test the next one, right? And you can solve that however way you want. You can solve it by graphing and looking for an intersection. You can solve it by adding your 6 and then doing the quadratic formula, whichever one makes your heart happy. Subtracting your 6, not adding. Okay. I can't accept this 4. I was trying to ignore it, but. Okay. All right. How do we feel about being given our y and having to work backwards? Not bad. Okay. Then it says, use the figure to find the point of diminishing returns and interpret its meaning. So our point of diminishing return is right here. That's the point when our two equations are equal. Do we see that? So we're looking for at what point do these two equations equal each other? That's our point of diminishing returns. So that's me setting 2x equal to negative 1/4 x squared plus 4x minus 4. Okay? You have again, could I get one side equal to 0 and use the quadratic formula to solve this? Yes. That is also an option. The other option is I can just get it equal to 0 and then look in the calculator for my x-intercepts, right? So I can subtract 2x from both sides, subtract 2x, and I'm left with 0 equals 1/4 x squared plus 2x minus 4. And I would take that to my calculator. And we're looking for the diminishing return. And our diminishing return is when these two functions are equal to each other, right? So here's my handy dandy calculator. I'm going to go here to y. I'm going to put in negative 1/4. My negative did not make it in my writing. Negative. So I'm putting in negative, and I don't have the fraction feature, so I have to protect my fraction with parentheses. 1/4 x squared plus 2x minus 4. I'm going to hit graph. Sylvie's going to do her thing. And I'm going to find my 0. So to find my 0, I'm pressing second trace, and you see 0. I'm going to go to the left of where I think it is and press enter. Then I'm going to go to the right. Go, spider, go. And press enter, and it says my diminishing value is at 3.99999, which is basically 4. So we end up with our diminishing value. Our point is at 4, 0. Well, it's at 4, sorry, not 0. Yes. So it's at x equals 4. Now, the return to get the full point, I would have to take 4 and plug it into the equations, right? So when I take 4 and plug it in, I'm going to use the easier one. And what's 2 times 4? 8. So our actual point is 4, 8. Oh, I wrote it behind the calculator. That doesn't help for you. So that means, so what does that mean? That means that the sweet spot, where we should stop is at 400 votes, right? If at 400 votes and they're bringing in 8,000 tons of fish harvest, and we maintain that, then we won't enter into our diminishing returns, which means that we're taking too much fish and not able for the fish to repopulate in time. Make sense? Okay, that's our real world example of a piecewise function. Do you guys have any questions, comments, or concerns about any part of what you learned today?